Hi, I'm Moroz, and I'm going to present my research predicting diffusion of TV news in social networking services that was done in collaboration with my colleagues Sergei Pashakhin and Sergei Koltsov from Laboratory for Social and Cognitive Informatics, Higher School of Economics University. We live in a world that is overloaded with different kinds of information circulating in various digital environments, where it can be freely accessed and shared. Once some content is released and gets reshared, we can talk about information propagation. This resharing event can occur only once, and then it goes mostly unnoticed. But when it occurs several times, involves multiple users connected via propagation pathways, thus forming a network with a hierarchical structure. We call it a propagation cascade or a propagation tree. And start to study it. Cascades may vary in size, and they rarely become large. In the last 2 decades, there were several attempts to model this variation and explore the factors which contribute to its prediction. In the current research, there are 2 approaches that can be outlined. It is generative approach and feature-based approach. Generative approach involves characterizing and simulating the process of information getting reshared. Models have excellent interpretability, but unfortunately they predict poorly the variation in cascade size observed in real-world networks, online networks. Feature-based approach, on the other hand, sees modeling of information diffusion as a regression task, where a numeric value gets predicted, or a classification task, where we predict class labels, involving a learning algorithm and a set of predictive features. It provides opportunities for both prediction and interpretation. In line with the feature-based approach, several points have been made. First of all, there are a lot of different versions on which features are the most essential for predicting of information cascades size variation. Some authors claim that it should be content features involving such characteristics as word frequencies in content posted or presence of hashtags and attachments or some topical content. Others claim that content features are weak predictors, and average connectivity of first posters and structural and temporal features should be used for enhancing the predictive ability of the models. Also, there is a work that states that all feature categories are important and none of them is masked under the presence of other feature types. When we talk about feature contribution to the model predictive ability. The second point is that nonlinear, more complex algorithms in general perform better than linear ones, better capturing the predicted variation. Finally, the highest proportion of variation explained by the model in the outcome is reported as less than 50%, but is about the metric called R-square. A lot of works used other metrics which calculate the size of the mistake, but just base the model during the prediction on the unseen data. But we cannot really compare all the works by these metrics because they imply different range of values of the outcome. We base our research on the feature-based framework, considering prediction of information diffusion as a regression task. We measure information propagation as a cascade size, implying 3 different metrics of its structure: mass, width, and depth. Mass is then defined as the total number of nodes at all levels of resharing cascade. Width is the biggest amount of nodes at one of the levels of resharing cascade, and depth is the maximum number of levels in a resharing cascade. I tried to draw some pictures which can help to illustrate the terms. So, for example, in case of cascade's depth, its corresponding picture has 3 nodes colored in red. In total, so number 3 in this case would be the value of cascade's depth. The same logic with the quantity of red nodes can be applied to other pictures and terms. The data used to conduct this research comes from the most popular Russian social networking service, Vkontakte. We sampled top posts from official communities of Russian state television channels and gathered the data that eventually constituted feature set and the outcome levels. Among these data, there were reposting data, which is the chains of reposts for top posts from the channels, reposters data, which is publicly available profile information of users who reshared one of the top posts at least once at any level of a cascade. Then channel statistics, which is the total number of post comments, likes to comments. In this case, by posts, we mean those top posts. Then popularity figures for each post, like the post's number of likes, comments, and reposts. And finally, topic modeling data gathered from the topic modeling procedure that my colleagues conducted in their another research. It included probability distribution for 86 labeled topics, so that we would get 86 columns, each containing a distribution of probability of belonging to one particular topic, of a content belonging to one particular topic. The dataset used for training and assessing models consisted of about 100 of predicting features and 3 outcome variables. The features can be grouped into 4 categories: root post features, channels audience features, and contextual features. So I will take a sec. Here you can see which features exactly constituted these 4 categories. Yep. Then the unit of observation in this dataset was a post in the channels community with almost 4,500 observations total. The eventual dataset consisted of 14 channels. Their names you can glance from this table. Also, there are some figures like number of posts, reposts, and maximum values of the outcome variables in the last 3 columns. The methods that were used for model building include linear and non-linear machine learning algorithms. In case of linear algorithms, we used penalized regression, as we had quite a lot of predictors and risked to face an overfitting issue. Also, the dataset for these linear models was normalized with the scaling procedure, as our target variables were non-normally distributed. They followed a power law distribution, and those violated linear regression models assumptions. The data itself was also split on the training and testing sets. The first one was used to build models, and the second one was used to assess their performance. We split the data by date, so that the earlier posts we would get into the training set, and we would assure the external validity of our model's predictions. Also five-fold cross-validation on the training set was applied. For assessing variables contribution, we used variable importance scores and relative influence scores. For inferring the direction of features influence, standardized regression coefficients in case of linear models were used, and when we needed to assess the same effect of features used in the black box models, we use partial dependence plots. For each outcome, thus we constructed 9 models, with 6 of them trained and assessed on the normalized data. As for results that we got, first of all, nonlinear algorithms, like more complex ones, performed better in general than linear ones. Secondly, models' performance was astonishing at first. Models predicting width and mass of a cascade were accounting for almost 100% of variation in them, while models predicting depth for almost 60% of variation in it. However, after we looked at the features contribution, which I'll show a bit later, and removed the most influential feature, the R-squared dropped significantly. So in the table, you can see the performance indicators for the best fitted models with the full feature set, which are colored in red, and with a feature set with one feature removed, which are colored in blue. So, for instance, on the example of R-squared value, the difference is obvious and quite sharp. So the feature that was the most influential was the number of reposts on the very first level of a cascade. This number, which all users can see if they go and look at any post on the community wall, along with the number of likes, comments, and views for this post. It can be called an indicator of the first level information propagation, though it doesn't give anything on the structure of this propagation, in contrast to our outcome variables. Yet it can be said that the eventual structural cascade size variation can be successfully predicted by this feature only. Now to the features contribution. I'll start with the mass of the cascade. So these graphs below that you can see, they are showing features contribution. Not all of the features used in the models are displayed. There were, as I said, more than 100 of features. Only top ones are present, sorted by their influence. The left graph shows the best fit model with the number of reposts on the first level, while the graph on the right displays the best fitted models with this feature removed. Later on, I will call the graph on the left the first scenario, and the graph on the right the second scenario. So not to get confused. The difference in amount of influence of predicting feature in the first scenario is quite evident. Yet we can say that all categories of features appear as among the most important for the prediction in the first scenario, while in the second scenario, only contextual features and channels and its audience features are on the top. Contextual features, in our case, are topics, probabilities of belonging to one of the topic. As you can remember, channels features are something like total number of channels comments to posts, and the audience features are for example, cumulative number of followers. Yep. Now to the features direction of influence on the outcome variable. So in case of Cascades mass prediction with the full feature set, the first scenario, we can see that such features, such top influencing features as the number of posts, reposts, the cumulative number of followers, the total number of likes to channels posts, the average age of channels followers, probability distribution of belonging to the topic policy and policy making, and two another topics, has a positive relationship with an outcome, while surprisingly such features as channels for prevailing followers sex indicated as male, which is a channel's audience feature, and the number of channels followers, which is channel's audience, again, no, this is channel feature, yeah, which is channel feature. They have a negative influence on the outcome variable, meaning that, for example, an increase in the number of channels followers will be followed by a decrease in Cascades mass. This is quite unusual, I would say, and channels followers sex indicated as male having a negative impact on the Cascades mass Cascades mass can be allegedly explained by male users' tendency to less frequently become intermediate recipients or brokers of information in a diffusion network. But this is only our hypothesis about the received results. And of course, further research is needed to establish such a connection. Next is the prediction of cascade mass with one feature out. So this is the 4 top features displayed on the partial dependence plots. Partial dependence plots show the marginal effect of a predictor on an outcome variable, like in any case. So marginal effect is on the y-axis in our case. If lines that are present on the graph are higher than the 0 point on the y-axis, then we can say that a predictor has a positive effect on an outcome variable, while if it is below the 0 value on y-axis, then it has a negative effect on an outcome variable. Multiple black lines here are trees that were built during random forest prediction or gradient boosting prediction in case of the upcoming plots of the same type that I will show later, while the red line stands for the averaged predicted values. So meaningfully, we can see that these top features have mostly positive effect on an outcome variable as a cascade. Some of them even have probably no effect until some point. Going further, we have cascades with prediction, the similar graphs showing features contribution. In the first scenario here, there is even more drastic difference between contribution of other features compared to the number of posts reposts on the first level of resharing. The conclusion about the first scenario is, though, about the same. All categories of features are among the most important in prediction of cascades with. While in the second scenario, we can see that only content features, and topics and the channel's audience features, like the cumulative number of followers appear on the top as the most important. Now to the PDP plots again. So here, nothing special, I guess. All of the features that were, well, most of the features that were present on the previous blue graphs show positive association with an outcome variable. Finally, Cascades depth prediction. The very same logic again, first scenario, second scenario. In the first scenario, again, all categories of features appear on the top as the most contributing, while in the second scenario, the conclusion is about the same as it was with the very first mass of a cascade when we discussed it. Contextual features and channels and its audience features are among the most important ones. And now, when we come to see the direction of features influence on the cascade's depth, we see a strange thing again. We see that popularity figures of a channel or channel's features group tends to have a negative impact on a cascade's depth, as we see that marginal effect is below the 0 point for all three features displayed here. We can, of course, speculate that such a phenomenon can be linked to the reputation of the chosen channels and their representation in the chosen social network of Contacte, as we would hypothesize that the online channels are perceived by users of the social network as not trustworthy enough to participate in spreading of its content. But again, it is only our little theory that needs to be provided with some evidence, some evidence from further research. As for the second scenario with one feature out, in Cascades depth prediction, we see about the same picture again, total number of comments to channel's posts as a channel feature shows a negative association with an outcome variable, while other types of features are positively related to it. So that's basically it about the results. Some of them are pretty logical, while other ones are surprising. And I guess I will continue on investigating the reasons behind such results in my further contributions to this topic of predicting information propagation and factors that are related to it. As for this research and its findings, they of course have some limitations. One of its limitations is that the results cannot be generalized on reposting patterns of any other content on social media networks, except for news data, as we used news data from Russian television channels. Another small limitation would be that it is quite debatable whether the R-squared value can be applied for assessment of complex black box models, predictive ability, gradient boosting, and random forest in this case. Perhaps there are other limitations that we missed, but these ones are among the most salient limitations. So that's basically it, what I wanted to present. Thanks for your attention, and me and my colleagues will be glad to answer your questions in any form they come.